So in the same way we looked at RC circuits, a resistor and a capacitor combined in series with a battery, now let's come back and look at our L circuits. So we're going to take a resistor and an inductor and connect them in series with a battery. So here's our basic setup. You can see there's the battery with the voltage V. There's a resistor, resistance R. There's an inductor, inductance L. And again, all three of these things are constant, right? So you're not going to change the voltage of the battery, the resistance of the resistor, or the inductance of the inductor. So we said at t equals 0, the inductor is going to act like a broken wire, because basically what it's going to do is it's going to generate a back EMF. There's no current flowing through it while the switch is open. So it's going to generate a back EMF so that no current flows through it at t equals 0. So here you go, you get the inductor to generate a back EMF. So there's no current, but you do have a non-zero di dt. So the current is starting to change. And again, this just comes from the equation for how we calculate the EMF, right? It's equal to L di dt. So if you have a non-zero EMF, you have to have a non-zero di dt. So when we go ahead and use the loop rule, as we go around, right, we're going to have as we start down here in this corner, and we go in this direction, which again is going to be the direction of the current flow once it starts flowing. We're going to get a positive voltage across the battery. We're going to get a negative voltage across the resistor because we're going in the direction of the current. And we've got a negative voltage across the inductor because, again, it's generating a back EMF. That gets us back to where we started. So our loop rule tells us that the voltage of the battery minus the voltage of the resistor minus the voltage of the inductor has got to be 0. Well, we know that we can deal with the voltage of the resistor by taking I times R. And so we just sort of plug that in, and that's going to give us this equation. And when we take the derivative of this equation, so again, what we see is, well, if I take the derivative of the voltage of the battery, that's constant, so the derivative of that with respect to time is just 0. The resistance of my resistor is constant, so when I take the derivative of this term, I'm only going to worry about the derivative of I with respect to time. And then I'm going to take the derivative of the voltage over the inductor with respect to time. So this is what I get when I take the derivative of this equation. Again, I can solve this for dVL dt, so take this over the other side. I'm left with this. And then again, we know that di dt is related to the voltage across the inductor. Right? So the voltage across the inductor is equal to L di dt. So when I basically solve that for di dt, I get V over L, plug that in, the L goes on bottom, the V goes on top. So this is what I get basically from rearranging, taking the derivative of my loop rule, and then rearranging and solving for the time rate of change of the voltage across the inductor. So what do I want to do with this equation? Well, again, I'm going to end up solving, and this is a differential equation, so what I want to do is get all the voltage terms on one side and everything else on the other. So when I rearrange this, I end up with this expression. It says dVL over VL equals negative RL over dt, and so I'm going to integrate both sides of the equation. I'll integrate the left-hand side from some initial voltage to the voltage as a function of time. I'll integrate the right-hand side from 0 to t, and again the minus r over L, those are all just constants. I pull those out of the integral. I'm left with the integral of t from 0 to t, or the integral of dt from 0 to t, that's just t. And then, so that gives me minus RT over L on this side. And then when I deal with the right-hand, or the left-hand side of the equation, again, I know that the antiderivative of dx over x is the natural log of x. So the antiderivative of dVL over VL is just the natural log of VL. And then when I evaluated the endpoints and use the properties of the natural logarithm, this is the expression that I get. And so all I want to do is solve this for the voltage over the inductor. And so again, I undo the natural log by taking both sides of the equation, plugging them into the exponential. So I want e to the power of natural log of VL over V naught, which is just going to give me VL over V naught. And then do the same thing over here, e to the negative RT over L, and that just gives me e to the negative RT over L. So the only thing left to do is just multiply over the V naught term, and now I have the voltage over the inductor as a function of time given by this expression. So what do I learn from this? Well, again, the first thing I do when I look at this is I say, well, again, T I know has units of time, which means that L over R, which is basically if I take the R and bring it down on the bottom, that's going to be L over R. L over R also has to have units of time. So L over R is what's known as my inductive time constant. So we talked about tau sub C, the capacitive time constant. This is tau sub L, the inductive time constant. Again, it's just the inductance divided by the resistance. Again, you can do a dimensional analysis to see that this in fact does have units of time. And so I can rewrite this expression as the voltage of the inductor. It's just going to be some initial voltage value times this exponential e to the minus t over tau, where tau is now given by L over R. So what this means is that the inductive time constant is the time it's going to take for the current to rise to 63.2% of its final value. So when we look at a plot here, again, V is the voltage of the battery. That's a constant. And what you see is that initially at t equals 0, the inductor generates a back EMF equal to the voltage of the battery, which is why there's no current at t equals 0. But that drops off exponentially by this equation. On the other hand, the voltage across the resistor, well, initially there's no current. At t equals 0, there's no current, so the voltage across the resistor is 0. But the voltage across the resistor is given by V equals IR, and as the back EMF drops, the current grows. And so this V equals IR is basically growing due to the fact that the current is increasing through the circuit as the back EMF dies out. And so the way it dies out is that at one time constant, the back EMF of the inductor has dropped to 36.8% of its initial value, and the current has risen to 63.2% of its final value. And then as t approaches infinity, what you see is that the voltage across the resistor effectively becomes equal to the voltage of the battery, and the voltage across the inductor goes to 0. So again, once you get past about 5 or so time constants, you're effectively talking about the voltage across the inductor has dropped to 0. So let's come back and deal with that initial condition, right? What's V naught in this case? Well, if you look at our initial circuit, and we said at t equals 0, our inductor acts like a broken wire, which means that basically this is the circuit that we have. And so when we use the loop rule across this circuit, well, what we see is that the loop rule at t equals 0 tells us that, well, if there's no current, which there won't be if this wire is broken, so if there's no current flowing through the circuit, then there's no voltage drop across the resistor. So if we start down here in the bottom left-hand corner as usual, we're going to pick up a voltage across the battery. There's no voltage drop across the resistor. And then we have the voltage across the inductor. And so this gives us at t equals 0 our loop rule that says the voltage of the battery minus the voltage of the inductor is 0. Well, so this is easy to figure out that the initial voltage across the inductor at t equals 0 is just equal to the voltage of the battery. And so we can go plug that in, and so that we get that our voltage across the inductor at t equals 0 is just given by the voltage of the battery times our e to the minus RT over L term. So if we want to think about the current through the inductor at any point in time, well, again, our loop rule says, well, if at any point in time means that we do have current flowing through the inductor now, or we do have current flowing through the circuit. So again, we have an increase across the battery, a drop across the resistor, a drop across the inductor due to the back EMF. And so now I can solve this for the voltage across the resistor. I know that I can use Ohm's law so that I get IR for the voltage across the resistor. And again, plugging in what I know, this is going to be the voltage of the battery minus the voltage across the inductor, and this is the expression I have for the voltage across the inductor. So it's the voltage across the battery, voltage of the battery times this exponential term. And so basically I'm going to factor out the voltage of the battery. I'm going to divide by R, so I get the current at any point in time. The current as a function of time is equal to V over R times this 1 minus e to the minus RT over Lt. So again, as t increases, this term goes to 0, and I get that the current is going to end up reaching a final value that's effectively equal to V over R. And that's what this graph right here shows, is that this plot, when you plot this function out, what you get is something that initially is 0, but is going to grow exponentially and then end up turning over so that your final value for the current is simply equal to voltage of the battery divided by the resistor. So at t equals 0, no current through the circuit, right? You plug in t equals 0 here, you get e to the 0. E to the 0 is 1. 1 minus 1 is 0. So initially there's no current through the circuit. That's consistent with the equation we just derived. It's consistent with the idea that at t equals 0 there's a back EMF due to the inductor, which basically is why it's acting like a broken wire. Once you get to a single time constant, then the current has already grown to 63.2% of its final value. And then as t approaches infinity, the current is going to be equal to simply V over R, as if this were now a complete wire, and so you simply had a single circuit where there's just one element, the resistor. So just summarizing what we're dealing with RL circuits, when you sort of set them up and then close the switch and start running current through the circuit. So again, as the current increases, what's going to happen is, the rate of the change of the current will decrease. So initially it's very large, but it's going to end up decreasing, which means the current's going to go up, but dIdt is going to go down. So the voltage across the resistor will increase, and the voltage across the inductor will drop. So here is our current, right? The solid line here is the current. The dotted line is the voltage across the inductor. And so again, at t equals 0, the current is 0, the voltage across the resistor is 0, and the inductor is generating a back EMF that's equivalent to the voltage of the battery. But it can't keep that up, and so that back EMF ends up dropping. As the back EMF drops, the current rises. And so you end up with a final scenario as t approaches infinity, where the current approaches just the value of V over R, and the voltage of resistor approaches the value of the battery, the voltage of the battery, because the voltage across the inductor has dropped off to 0. So that's the idea behind what's going on with RL circuits. Again, they're very similar to what's going on with RC circuits. We're just sort of, how you change things in terms of swapping out the capacitor for the inductor is changing whether as you charge an RC circuit and the current is dropping. Here, with an RL circuit, the current is increasing. The voltage across the inductor is dropping.